In 2018 and 2019, Boeing faced one of the most significant challenges in aviation history. Two Boeing 737 MAX aircraft experienced operational difficulties within 5 months of each other. These events led to a worldwide suspension of operations for the entire fleet and triggered extensive investigations. But here's what most people don't know. The investigations revealed that this wasn't a technical failure. It wasn't a software bug that slipped through testing. It wasn't one person's mistake. This was a systematic project management failure. A pattern of decisions that prioritize deadlines over safety, business constraints over engineering judgment, schedule pressure over technical reality. How does this happen? How does a project go from boardroom approval to billion-dollar disaster? What warning signs did people miss? What red flags were ignored? And most importantly, could this be happening in your project right now? By the end of this investigation, you'll see 3 critical decisions that led to this failure. You'll understand the exact warning signs that appeared months before the problems emerged. And you'll learn how to recognize these same patterns in your own projects before it's too late. Because what happened at Boeing isn't unique to aviation. It's not even unique to large corporations. The same pressures exist in your projects. The same decisions get made. The same warning signs get ignored. Let's investigate. This is Project Autopsy. Boeing 737 MAX. The investigations revealed something valuable for anyone managing complex projects. The failures that led to these events were preventable. Engineers had identified issues. Test pilots had documented concerns. Warning signs existed throughout the development process. But those warnings weren't adequately addressed. So what really happened? How does a company with over a century of aviation excellence produce an aircraft that encounters such serious problems? To understand this, we need to go back to 2011, when Boeing leadership faced a critical business decision. The year is 2011. Boeing has dominated the narrow-body aircraft market for decades with the 737. It's their most successful product line. Then Airbus announces the A320neo, a more fuel-efficient version of their competing aircraft. Airlines respond enthusiastically. Orders start coming in for the Airbus model. Boeing faces a strategic decision. They have 2 options. Option 1, design a completely new aircraft from scratch. This is the ideal engineering solution, but it would take 7 to 10 years and cost billions in development. Option 2, modify the existing 737 with new, more efficient engines. Much faster to market, much lower development cost. Boeing chooses option 2. Here's where the project constraints become critical. The new engines are larger and must be mounted differently on the wing. This changes how the aircraft handles. Specifically, it affects the pitch characteristics during certain flight conditions. But Boeing positions the 737 MAX as requiring minimal additional pilot training. Why? Because extensive training requirements would significantly reduce the aircraft's appeal to airlines. So Boeing engineering receives a constraint from leadership. Make whatever technical changes are necessary, but make them transparent to pilots. Make the 737 MAX handle like previous 737 models. The timeline: deliver the first 737 MAX by 2017, 6 years. The business case depends on meeting this timeline. Finding number 1. Business deadline established before technical solution validated. Boeing committed to a delivery date and a training promise before fully understanding the engineering implications. The project constraints were business-driven rather than engineering-driven. So how do you address handling differences without requiring extensive pilot training? You implement automated software that corrects the issue in the background. Boeing creates MCAS, the Maneuvering Characteristics Augmentation System. When sensors detect specific conditions, MCAS automatically makes corrections. The pilot doesn't need to intervene or even know it's operating. This appears to solve Boeing's challenge perfectly. The aircraft handles differently, but software compensates automatically. Minimal training required. Business case preserved. But here's the critical design decision. MCAS relies on input from a single sensor. Just one angle of attack sensor that provides data about the aircraft's orientation. Any engineer will recognize that depending on a single sensor for a critical system creates risk. What happens if that sensor malfunctions or provides incorrect data? If the sensor fails, MCAS could make inappropriate corrections based on false information. Engineers identified this risk. Internal documents show this single point of failure was explicitly discussed during development. Adding redundancy, requiring multiple sensors to agree, was considered. But that would increase complexity, more testing, extended certification timeline, possibly requiring additional pilot training. The decision was made. Single sensor design is acceptable. The timeline takes priority. Finding number 2. Known technical risk accepted to maintain project schedule. Those solutions were not implemented because they would impact the project timeline and training requirements. Business constraints overrode technical concerns. During flight testing, Boeing test pilots discovered that MCAS behavior could be unexpected under certain conditions. That if activated in specific scenarios, it could be challenging to manage. They documented these findings. However, this information wasn't fully incorporated into the operational manuals that airlines received. It wasn't emphasized in training materials. Many operational pilots had limited awareness of MCAS functionality. Why? Because comprehensive documentation and training about MCAS would raise questions. It would require explanation and training time. And training meant the minimal training requirement promise would be compromised. So Boeing's approach was to make MCAS so reliable and automatic that comprehensive pilot training wouldn't be necessary. In October 2018, during a routine flight operation, a sensor malfunction occurred on a Lion Air 737 MAX. The faulty sensor provided incorrect data to the flight control system. MCAS responded based on that incorrect data, creating a challenging situation for the flight crew. After this event, Boeing issued guidance to airlines about existing emergency procedures. However, it wasn't classified as a critical safety issue requiring immediate fleet action. 4 months later, in March 2019, a similar sensor malfunction occurred on an Ethiopian Airlines 737 MAX, again creating operational challenges. Following these 2 events, aviation authorities worldwide suspended operations for the entire 737 MAX. Finding number 3. Critical system information not adequately communicated to operational users. Boeing test pilots understood MCAS behavior under various conditions. That knowledge wasn't fully transferred to airline pilots to maintain the minimal training narrative. So what was the root cause of the Boeing 737 MAX situation? After extensive investigation, the evidence points to a systematic pattern. Project schedule and business requirements consistently took precedence over technical considerations at key decision points. Let's trace the decision sequence. Decision 1. Modify existing aircraft instead of new design. Rationale: faster market response, lower development cost. Decision 2. Promise minimal pilot training to increase market appeal. Rationale: training costs are significant airline concerns. Decision 3. Implement automated software to address handling differences. Rationale: if software handles it automatically, pilots don't need extensive training. Decision 4. Use single sensor despite identified risk. Rationale: adding redundancy increases complexity and timeline. Decision 5. Limited documentation and training about MCAS. Rationale: extensive documentation would require training, contradicting the minimal training promise. At every decision point, Boeing chose the path that protected the project timeline and business case. This represents a project management failure, not merely an engineering mistake. This wasn't one individual making a poor choice. This was a systematic culture where project deadlines and business objectives consistently outweighed technical concerns. When engineers raised safety issues, the response focused on, how do we address this without delaying the program? When test pilots documented concerns, the response was, can we handle this through procedures rather than redesign? When the business case required minimal training, that became a non-negotiable constraint that engineering had to accommodate. The project served the deadline, not the mission. After the operational suspension, Boeing spent nearly 2 years implementing changes to the 737 MAX. They redesigned MCAS to use multiple sensors. They made it less aggressive and easier to override. They added cockpit alerts for sensor disagreements. They made the system more transparent to pilots. And they implemented comprehensive training programs. They restructured their safety oversight processes. They changed how engineers could escalate concerns. They modified how project pressure could affect technical decisions. The financial impact was substantial. Development costs, compensation to airlines, production impacts, and regulatory expenses exceeded $20 billion. So what can you apply from this case study to your projects? Lesson 1. Establish non-negotiable parameters. Every project has constraints. Timeline, budget, scope, resources. This is normal project management. But certain things cannot be compromised under any circumstances. For Boeing, safety should have been the absolute, non-negotiable parameter. Everything else should have been flexible around it. In your projects, identify your equivalent. What's the one thing you will not compromise, regardless of pressure? Is it data security, user privacy, system reliability, regulatory compliance? Document it explicitly. Make it visible. Include it in every project document. When stakeholders request shortcuts, you point to that parameter and explain. Everything else is negotiable. This isn't. Lesson 2. Address single points of failure. Boeing's single sensor design created a critical vulnerability. When that sensor failed, the system failed. In your projects, systematically identify single points of failure. Ask, what single component, if it fails, compromises the entire system? Is it one database, one server, one vendor, one key team member, one assumption? Then determine, can we implement redundancy? What's the cost of not having redundancy? The time to identify and address single points of failure is during design phase, not after system deployment. Lesson 3. Create channels for concerns. When Boeing engineers identified MCAS issues during testing, there was pressure to minimize them, pressure to resolve them without impacting timelines or complicating certification. This is a critical moment in most projects. When someone identifies a significant issue, the team faces a choice. Raise the alarm and potentially delay, or work around it and hope it doesn't manifest in production. The pressure is always to choose the second option, to minimize, to patch, to maintain schedule. Create a culture where concerns surface immediately, where people can identify risks without negative consequences, where raising issues is seen as protecting the project. One practical technique: conduct a pre-mortem session before launch. Gather your team. Ask, imagine we launched and it failed significantly. What would have caused that failure? Have everyone document their thoughts privately, then share them. People will voice concerns in this hypothetical that they might not raise directly. Listen carefully. Evaluate each concern. Then decide, can we launch with these risks, or do we need to address them first? How do you recognize if your project is following a similar trajectory? Watch for these indicators. Indicator 1. Business requirements consistently override technical recommendations. Launch dates are more important than system readiness. Indicator 2. Technical staff raise concerns that are dismissed as overly cautious or not collaborative. Indicator 3. Testing is compressed to meet deadlines. The plan includes testing in production or relying on users to identify issues. Indicator 4. Known risks are documented but not addressed. The assumption is these will be resolved in future versions. Indicator 5. Success is primarily defined by meeting schedules rather than delivering quality outcomes. If you observe multiple indicators, pause and reassess. Have direct conversations with leadership about priorities and acceptable risk levels. The Boeing 737 MAX returned to service in November 2020 after comprehensive modifications and new certification processes. The aircraft now operates successfully with the implemented changes. But the cost was substantial. 2 years of development. $20 billion in expenses. Complete restructuring of safety processes. The situation was preventable. Warning signs existed. Engineers identified issues. Test pilots documented concerns. But project timeline pressure was intense. Business case requirements were firm. Competitive pressure was significant. This case study demonstrates an organizational and cultural challenge, not primarily a technical one. Schedule pressure over safety considerations. Business constraints over engineering judgment. Project deadlines over comprehensive risk assessment. This is Project Autopsy. Every week, we analyze significant project failures and extract lessons applicable to your work. Next week, we examine another case study. Target $7 billion expansion challenge, a supply chain implementation that led to unprecedented retail difficulties. Subscribe so you don't miss it.